Hello, in this video I wanna teach you how you can simulate a flat plate solar collector conjugated heat transfer CHT using ANSYS Fluent software. Flat plate solar collectors FPSC are widely used in the solar industry to convert solar radiation into thermal energy. The efficiency of flat plate solar collectors depends on various factors including the design of the collectors, the material used, and the collector's location. In this simulation, we investigate radiation's effects on the water's temperature passing through pipes in an FPSC located in Doha with a 15-degree tilt angle at 3 different hours during a day in August using ANSYS Fluent software. The simulation was conducted for 3 different hours on August 10th, 12 p.m., 3 p.m., and 5:30 p.m. The solar radiation intensity at these times is different due to changes in sun angle and atmospheric conditions. The geometry of this project was defined using ANSYS SpaceClaim software and meshed using Fluent Meshing software in Polyhedra type. It must be noted that the whole number of elements created is 2,871,429. Open the ANSYS Fluent software. At first, you must read the mesh file. There are 3 main assumptions in the simulation. At first, we have used the pressure-based solver due to the incompressibility. This simulation has been done as a steady state, and we have considered a gravity effect in the z direction. Due to the fact that there are temperature changes in the simulation, the energy equation must be activated. Okay, now let me show you how you can set your turbulence model for the simulation. Here, as can be seen, I have chosen K epsilon realizable with the standard wall function. Actually, the realizable K epsilon model is an enhancement of the standard K epsilon model of turbulence, which is widely used in CFD simulation, including in ANSYS Fluent. This model aims to improve the accuracy for flows involving rotation, boundary layers under strong adverse pressure gradients, separation, and recirculations. The realizable K epsilon models actually modifies the standard K epsilon model by introducing a new formulation for the turbulent viscosity and a new transport equation for the dissipation rate. There are some advantages of the realizable K epsilon models. It provides better performance for flows involving rotation, boundary layers, and separations, and the model has been found to give more accurate predictions of the separating rate of both planar and round jets. It does a better job of predicting the flow direction for highly swirling flows compared to the standard K epsilon models. And about standard wall function. Actually, the standard wall function in ANSYS Fluent is a method used to bridge the gap between the near wall region of a turbulent flow and the fully turbulent region away from the wall. This is necessary because resolving the entire boundary layer directly with a fine enough mesh to capture all the turbulent fluctuations and can be computationally expensive, especially for complex geometries or high Reynolds number flows. The standard wall function approach is based on the law of the wall, which describes the velocity profile of turbulent flow near wall. It assumes a logarithmic velocity distribution in the inertial sublayer, which is the region above the viscous sublayer and below the fully turbulent flow. Okay, now here, enable the discrete ordinates radiation model, DO radiation model. Actually, the discrete ordinate model is one of the most accurate models for predicting radiative heat transfer in enclosure with participating media. It can handle isentropic scattering and non-gray extinction coefficients. The DO model solved the radiative transfer equation RT, for a finite number of discrete directions, hence the name discrete ordinate. In ANSYS Fluent, the DO model is implemented in a way that it can be used in conjunction with any of the flow and turbulence models and with the other heat transfer models. The DO model is suitable for predicting radiation in combustion systems, solar collectors, furnaces, glass manufacturing, and any other systems involving radiation through participating media. Please note that the DO model may require more computational resources as compared to other simpler radiation models due to the complexity and the nature of the calculations involved. I have defined the water, liquid, and glass materials before. Now I want to show you the properties of these materials. For the water, liquid, and air, and also the glass material. Okay, next step is the solvent conditions. There are 4 zones in this simulation. By clicking on each zone and click on the edit, you can see its dialog box, and you must set its related materials for each of them. For example, for water zone, you must specify the water liquid material. In the boundary conditions tab, by clicking on the display mesh, you can see this dialog box, and by choosing each of the surfaces, you can see the surface in the Fluent window, and also if you enable the edge, you can see the mesh on each surface that you have selected. All the boundaries can be seen here. Next step, double click on the residuals and enable all these boxes. Set the absolute criteria for each equation. When the remaining equations reach these values during solving, the software assumes that the solution has converged and stops it. Note that the criteria is the smallest number. For example, here for the energy equations and radiation, DO intensity. And for the last step, specify the number of iterations and click on the calculate to start the calculation. After your solution is converged, right click on the contours, new, and here choose the temperature, and for the surface select the glass to see the temperature contours on the glass. Click on the y-axis to have 2D view. Here you can see in which area the temperature is high and in which area the temperature is low. Also, from reports, surface integrals using area weighted average. Set the temperature, and for the surface outlet, click on the compute. You can see the temperature in the outlet. As can be seen, the temperature after the solution is increased. To benefit from MR-CFD services, including simulation, consultation, and training, visit our website www.mrcfd.com and contact us via info@mrcfd.com.